Hello, in this one, looking at some techniques for simulating noisy amplifiers in the simulator. Right, let's get the simulator up. If you want to input a noisy component, it doesn't add the noise automatically for the components. So if you want to add a resistor and include the noise contribution of that resistor, you have to take an explicit noise voltage source. Make sure it's one of the AC ones, because noise is an AC signal. And then if you hit the Alt key and click on this symbol, the waveform will cycle through the possibilities. It's a sine wave at the moment, that's a square wave, that's a pulse waveform, and this is noise. You can tell it's noise because the value immediately goes to volts RMS per root hertz, and a little red line appears around the noise component, indicating that this is a noise voltage. The simulator needs to know that, so that when it combines noise contributions, it adds the powers, not adds the voltages. So that would be a model of a noisy resistor, except of course 1 volt RMS per root hertz is not the noise you get from a 1K resistor. You have to calculate the noise that you get from a 1K resistor. The simulator won't do that for you, so you have to calculate it yourself. Now, the noise power from a resistor in terms of its RMS voltage is square root of 4kT BR, but I'll just write that as R at the moment and not worry about the square root of B, because I'm going to be calculating the volts per root hertz, not just the volts RMS as a voltage. So that's given by this formula here. If we put in the values for that formula, square root of 4 times K, 1.38 times 10 to the minus 23, times T, we assume is its kind of standard laboratory temperature, which we usually assume to be 290 degrees Kelvin, and then multiplied by the value of the resistor. In this case, that is 1K. Plug all that into a formula, and we get square root of 4 times 1.38 times 10 to the minus 23 times 290 times 1K, 4 times 10 to the minus 9. So that would be 4 nanovolts per root hertz. Okay, we can just put that in here for N. And now we have a noise model of a 1K resistor. Op-amps are similar, but in case of op-amps you have to add noise currents as well. It's a similar process. We take an AC current, Alt-click on it until we get the noise current, and then set that to the value appropriate for the current that we're interested in. In the case of an op-amp, we'd look up on the data sheet to see what the noise current was, and that might be something like 0.01 pico or 10 femtoamps in the case of a typical high input impedance op-amp. We can add the 3 equivalent input noise sources to an ideal noiseless op-amp as well to produce a noisy op-amp model which looks like this. I've just tidied it up here a little bit, put a box around it to indicate that this is all a noise model of a typical op-amp. And then we can combine these circuit elements to produce models of noisy op-amp amplifier circuits. This is a noise model of an inverting op-amp. You can see that the figures that I've put in are correct for these particular values of resistors, although if I had to change the values of a resistor, I would have to remember to change the values of the associated noise sources as well. It doesn't happen automatically. Now, for the amplifier, I've just used typical figures for a TL071. Now, you can disable these noise sources one by one, and that will give you some idea of which are the most important contributions to the total output noise. That's done by pressing Shift and click. So if I Shift and click, on these noise sources and allow it to recalculate, you'll see that the output noise is now 0 because, as we've seen before, this equivalent input current doesn't contribute to the output at all. It's definitely negligible. This, however, input current does make a contribution. If I turn it on and this one off, we get a tiny amount of noise in the output, which is really insignificant compared to the effect of the voltage noise sources. The op-amp's equivalent input voltage source gives me almost 200 nanovolts out, which is getting on for 200 times the amount of noise that the current noise of the op-amp introduces. So these really are negligible. So that is a major contribution. The other major contribution is this one here, the source resistor. That's producing 126 nanovolts in the output. Output feedback resistor here, that's only producing 40 nanovolts, despite the fact that this is a larger resistor and therefore has a larger associated noise voltage with it. The difference is that the noise voltage associated with this resistor is not multiplied by the gain of the op-amp amplifier, whereas the voltage from this noise resistor, although smaller, is multiplied by the gain of the amplifier, which at the moment is a gain of 10. So these are the two most significant sources, contributing a total of 234 nanovolts. These two currents really are insignificant, and this noise feedback resistor here doesn't add very much. Really not a significant difference to the output noise adding that resistor in. You can make more complex models as well. This is a model of a differential input amplifier based on the MCP6291 op-amp with a gain of 36. And once again, we could turn all of the noise sources off and then go round one by one, seeing which ones were significant. The two current sources, they're both providing a little bit, but really not very much at all. Only about 1.5 nanovolts between them. The input equivalent noise voltage of the op-amp, much more significant, 321 nanovolts RMS per root hertz. The two input resistors contributing 453 nanovolts each. So they are now a bigger contribution to the output noise voltage than the equivalent input noise of the amplifier itself. The feedback resistor, only 76. The noisy resistor down here, another 76. Fairly negligible compared to the two input resistors, which at 10k are providing the majority of the noise. Turn those on and we get 641 nanovolts out. Add in all of the other contributions and it goes up to 725, which is not a huge difference, and most of that difference is caused by the input equivalent noise of the op-amp itself. It's quite fun and instructive to play around with these things. I should point out, if you haven't already noticed, you might have, is that if the largest contributions to the output noise are these two input resistors here, and we wanted to have a gain of 36 for our differential op-amp, then we could get a substantially smaller output noise if we just drop the value of all the resistors by a factor of 10. Replace the 10k resistors with 1k resistors and replace the 360k resistors with 36k resistors. If we do that, the noise voltage would drop by the square root of 10, and the output noise would correspondingly drop. At the moment, it's 788.6 nanovolts. What is it if we drop the resistors by a factor of 10, remembering to change their noise voltages as well? Well, let's try it. 12.6 nanovolts, if it drops by the square root of 10, would get you to 4 nanovolts per root hertz. And 76 divided by the square root of 10 would get you to around 24 nanovolts per root hertz. And that is the noise for a 36K resistor. And we've now got a differential amplifier with the same gain, 36, but the output noise is now 382, which is significantly smaller than 788. We've made a significant improvement in the noise performance of our amplifier. The disadvantage, of course, is now the currents in the circuit are larger, and this is a common trade-off in low noise design. You tend to want to have larger currents if you want to have a lower noise from the resistors in your amplifier. It also means the input impedance into your differential amplifier is correspondingly smaller, which may be an issue depending on the application. Okay, that's it for this time. Next time, on to a completely different subject, quantization noise in analog to digital converters.